So let's, instead of finding the percent composition from a chemical formula, let's go the other way. Okay, let's say that we know the percent composition of a compound, but we are not sure what compound that is or what its formula is. This is actually a lot more realistic as far as research and everything goes. You know, if you synthesize something, a lot of the times you've got to figure out what percent it is, carbon, hydrogen, oxygen, whatever, and then a slew of other tests and everything as well to be able to get more information to identify exactly what you are, or which chemical or compound you have either synthesized or have isolated to make sure that you get exactly what you want. There's lots and lots and lots of application of using the percent by mass or the percent composition to actually find the formula. So the first thing I want to do is kind of emphasize something from the slides, is that the empirical formula for methyl acetate, or for anything, the empirical formula is always going to be the formula that is in the lowest whole number ratio. And then we've got something called the molecular formula, which we'll look at here in just a minute. There are many, many compounds that might share the same empirical formula, but they do not have the same molecular formula. So their actual identities are very, very different, but they are just different multiples of the same ratio of elements. Okay. Here we're just going to look at that smallest whole number ratio, that empirical formula. Okay, so methyl acetate, we use it in lots of paints, inks, other adhesives. It kind of keeps things dissolved. It isn't necessarily, or you know, it's not necessarily something that is keeping things dissolved in like an aqueous solution, the way that you see that, where it's completely clear. Instead, it's just something that can be used to keep pigments from clumping and drying out, and that's something that methyl acetate is very useful for. So it doesn't necessarily mean that it's going to make paints, inks, or adhesives look like clear water solutions. Okay, so it is not water as a solution, it is a different compound. Okay, just some background information. Alright, so here, let's say that we put methyl acetate through a bunch of tests and we found the percent composition. We know that it's 48.64% carbon, we know that it's 8.16% hydrogen, and 43.20% oxygen. And we want to figure out what its empirical formula is. Now, if you notice, there is not a sample size. It doesn't say that I took 4 grams and got this chemical analysis. Instead, it just kind of leaves that up for interpretation, because it doesn't really matter my sample size if it's always going to be 48.64% carbon, 8.16% hydrogen, and 43.20% oxygen. It's going to have that same proportion, the same percentage ratio or relationship of mass of these elements in the compound, regardless of my sample size. And so that's something that is also very unique to pure substances. And compounds, remember, are pure substances. They have unchanging and universal, as far as throughout the sample itself, composition, so consistent composition as well. So since it doesn't tell you, and you know that regardless of the amount, you should always have this relationship percentage-wise, you can assume a certain amount of your sample. And you can assume really any amount, but for most of us, we like to say, well, these are percentages, so that means out of 100, so why not make this a 100-gram sample? And now, if I look at just carbon, 48.64% of 100 grams is now 48.64 grams of carbon. Okay, so if you're just given these percentages, if you assume 100 grams for your total sample size, you can take these percentages and put them into masses, okay, without changing the numbers at all. So you have no math to do for this step. If you pick any other number besides 100, you got to do some math. So it's just much easier to do this. Okay. For hydrogen, we would have 8.16 grams of hydrogen, and then 43.20 grams of oxygen. Okay. So remember, in a chemical formula, any chemical formula, it tells you the mole ratio of elements in 1 mole of that compound. So if I'm given mass of each element, I could figure out the mass, or not the mass, excuse me, I'm given mass, I could figure out how many moles that would be. So how many moles of carbon do I have, how many moles of hydrogen do I have, and how many moles of oxygen do I have if these are the masses that make up my compound? Okay, so to do that, you could use dimensional analysis to get out of grams of carbon and into moles of carbon. Okay, you can do it for the other two, and I'm actually going to change my color here in just a second to make it easier to keep up with. Actually, I might just bring stuff down. Okay. So if you notice, my grams of carbon cancel. I'm left in moles. And we know to get between moles and mass, I need to use the molar mass of carbon. And I know that 1 mole of carbon weighs 12.01 grams. Okay, this should give me my number of moles of carbon. All right, so actually, you know what? I'm going to show you this. I usually save all my calculations for last. Let's go ahead and set everything else up. So let me grab another color marker. I'm going to go back over this. So this is 8.16 grams of hydrogen. Okay. To get out of grams of hydrogen, I want to divide by its molar mass again, just like I did up here. So grams of hydrogen on bottom, moles of hydrogen on top. I know that 1 mole of hydrogen weighs 1.01 grams. Okay. And that should give me moles of hydrogen, just like this should give me moles of carbon present in my sample. Okay, let me grab one more color and we'll do the same thing for oxygen. Okay, so I want grams of oxygen on bottom. I can get into moles of oxygen with its molar mass. 1 mole of oxygen weighs 16 grams. So this is going to give me moles of oxygen in my sample. All right, let's do the math real quick. At this step, if you notice, I've always rounded my molar masses to 2 decimal places, and the percentages they gave me in this problem were just to 2 decimal places. But to make it a little bit simpler for us, let's always carry these numbers out to 4 decimal places, because sometimes it can get more finicky than it needs to be if you round too much. So here we're going to keep 4 decimal places. So I've got 48.64 grams of carbon, and that's going to be divided by its molar mass to be able to give me moles of carbon. So this many grams is 4.04. Okay, see how that's, I would say 499, but that 5 would round that 9 up, which would round that 9 up, which would round that up to a 5. So really it's going to be 4.0500 moles of carbon. Okay. Over here I've got 8.16 grams of hydrogen divided by 1.01 grams of hydrogen per 1 mole. Okay, so this many grams of hydrogen is 8.0792 moles of hydrogen. Okay. And oxygen, if I have 43.2 grams and divide it by 16, that's 2.7 on the dot, but I'm going to maintain that 4 decimal places. Okay. So once I have my moles of each substance from these percentages, I can then bring everything down. And let me grab a different color just so we can, I'm going to work everything in the same color now. Actually, you know what? I like the colors. Let's do this. All right. Now, that means that if I've got 4.0500 moles of carbon, okay, and 8.0792 moles of hydrogen, and 2.7000 moles of oxygen, I can see what's the ratio of moles of each of these to each other. Okay, the way that you do that is you find whichever element has the fewest number of moles present in your 100 gram sample and divide every mole by that number. Okay, that's going to give you the simplest ratio of moles of your elements. Okay, I see that I've got the fewest moles of oxygen, so I'm going to divide everything by the moles of oxygen. Okay, so right here, okay, and divided by 2.7000 moles. Okay, I know for oxygen that's going to give me still just 1 oxygen, or 1 mole of oxygen. Okay. Over here for hydrogen, I need to actually plug that in my calculator. So I'm going to take 8.0792 and divide it by 2.7000, which in your calculator, oops, excuse me, you don't need to necessarily put all those zeros in, but since I'm writing them down, I'm going to go ahead and plug them in. Okay, here I get 2.99. Okay, this is basically 3, and at this point we're looking for whole numbers as a ratio, so I'm going to assume that that's going to be good enough to be 3 moles of hydrogen for every 1 mole of oxygen. Okay, at this point, and we'll actually talk a little bit more about this in class, there's a certain kind of range of values that you can round up to the nearest whole number, certain range of values that you can round down to the nearest whole number, and certain values you need to keep at either intervals of like a third or halves. But that's something that we will kind of approach as we get to that point, and we'll work out in class as well. Okay, but here that's good enough to say 2 or 3, excuse me. All right, for carbon, I'm going to take this 4.0500 and divide it by 2.7000. I get 1.5. Oh, this is a good example. All right, see how I get 1.5? That means that for 1 mole of oxygen, I have 1.5 moles of carbon. Okay, that's not close enough. Like 2.99, that's 3. But 1.5, that tells me that this ratio here is good, but I don't have the lowest whole number ratio. Okay, when I see that half number, just like you did with balancing equations, you got to multiply everything by 2 if you have a half number. So it keeps the same ratio, but it puts it all into whole numbers. Okay, and when you do that, you're going to get 3 moles of carbon for every 6 moles of hydrogen, okay, and every 2 moles of oxygen. Okay. Now, once you know the exact whole number ratio of your elements in this compound, you can then take these number of moles and use them as subscripts after the element symbol to create the formula. So my formula would be C3H6O2. So methyl acetate has this empirical formula. So that's our empirical formula. All right, and notice this is the lowest whole number ratio.